Thanks. Good morning. We had just finished up the courses that describe the different compositions. And the last part of the course is on applications, which I've included quite a bit of slides on microstructures of refractories after use, so how they change during use. But before we do that, I thought I'd put one lecture on design. And there's two parts here. There's refractory design, how you design a refractory microstructure, including the chemistry, the mineralogy, which is the phases present, and how you put those phases together to form a microstructure, and a couple considerations for engineering design dealing with heat flow, expansion allowances, acid-base compatibilities, and then how you zone a refractory lining. So we'll do this today. And under refractory design, there's a size-based approach that really determines the properties. So you start out with the chemistry, which is the individual atoms. Then you go to the mineralogy, which are the phases present, the different crystal structures, the compounds that form. And then how you put those phases together is the microstructure. And that's where your phase equilibria comes into place and how these phases are assembled. That's all going to determine the final properties. And then for the design of these refractories, um, you start out with the coarse aggregates. Then you have to choose a matrix, the fines that form the matrix. You have to decide on the distribution, the size distribution of these aggregates and fines. And then you use the relevant phase diagrams to pick the right chemistry for the right application. And then for the engineering design, the specific application, what type of vessel is going to be used really determines the performance of the refractories. So for that application, you pick the refractories, and then you have to be concerned with heat flow, how much insulation, if any, you're going to use, the expansion allowances for the initial heating, and acid-base compatibility, what refractories are compatible in contact with each other, and what refractories are compatible with the environment. And then zoning, how you locate these refractories in a particular lining. So the first area is refractory design, and I'll go through some examples for chemistry. So the first example here is for solid solutions. And we've looked at this diagram, this phase diagram, a few weeks ago. So there's a chrome addition to an alumina refractory. So why do you add chrome? Because it improves the corrosion resistance. And an important application for this type of refractory might be coal gasification. In these units, the slag is often variable. It could be acidic or it could be basic. And the addition of Cr2O3 to Al2O3 just improves the corrosion resistance. So this is an example of an atomic substitution changing the chemistry. So again, the addition of Cr2O3 to Al2O3 for a fire break improves the corrosion resistance. And the phase diagram shows there's a complete solid solution of the Cr+3 ions as they substitute for the Al+3 ions. They're substituting on the cation sites and in a corundum crystal. The advantage of Cr2O3 is that it's more neutral than Al2O3. Al2O3, some people consider neutral, but it's slightly acidic. So Cr2O3 improves the corrosion resistance because it is neutral to both acid and basic slags. And in a coal gasifier, the slags are somewhat variable. The second example of chemistry is engineering the grain boundaries. So this is the second example I have, and we talked about the grain boundary phases and MgO aggregates. So the grain boundary phases basically are the bonds that hold the individual crystals in a polycrystal material together. And we looked at the MgO aggregates, the lime to silica ratio, and that application is for a basic oxygen furnace, or one of the main applications anyway. And we looked at the lime to silica ratio. So if this ratio of lime to silica was high, greater than 2.8, you form tricalcium silicate and CaO or lime. And those are high temperature materials. So the first liquids that form are above 1850 degrees C. And then when the lime to silica ratio drops between 1.87 and 2.8, tricalcium silicate and dicalcium silicate are present in the grain boundaries. So the liquid doesn't form till about 1790 degrees C. But when the lime to silica ratio drops between 1.4 and 1.87, you still have dicalcium silicate, but now you have a low melting phase, murrinite, and liquids are going to form at a much lower temperature, 1575 degrees C. So in a BOF, a basic oxygen furnace, that's below steel melting temperatures. And then we went on to say that this lime to silica ratio between 0.93 and 1.4, we have two low melting phases, murrinite and monticelite, and the liquid forms at much lower temperatures, 1490 degrees C. And then finally, for ratios less than 0.93, we have phosphorite, this magnesium silicate, and monticelite again, and it's still a low temperature system, 1500 degrees C. So you want to engineer the grain boundary phases in these MgO aggregates, these polycrystalline aggregates. So if the raw material doesn't have the right ratio for the intended application, which in this case would be a basic oxygen furnace, you have to adjust the chemistry. So you have to modify the lime and silica contents in the grain boundary. So that's an example of a chemistry example modifying a grain boundary. An example modifying the matrix. Um, we talked about alumina, MgO, carbon composites. These are resin bonded, and the alumina MgO is a spinel forming combination. An application might be in a ladle where this spinel formation controls the reheat expansion. So very simply, we talked about the alumina and magnesia reacting to form this magnesium aluminate spinel, MgAl2O4. Uh, there's a structural expansion. It's a lower density product. So the structure expands, and if you have these materials in the ladle, it tightens the joints in the ladle lining. So you have to choose alumina and magnesia raw materials with the desired degree of reactivity at whatever temperature the ladle is running at. So you have to choose how much free alumina and free magnesia is present and how much spinel will form. And that in that way you can control the reheat expansion. You can also start out with the spinel by itself. And you can also use the spinel, the magnesium aluminate spinel, in small amounts to see the reaction, to accelerate the formation of spinel. Another example, this is mineralogy. example in the matrix. And we talked about mullite formation in aluminosilicate fired bricks. And that also controls the reheat expansion and improves service life for ladles. So mullite formation is desirable in a ladle lining if you're using aluminosilicate refractories. Again, aluminum and silica reacts to form mullite. Uh, the product is a lower density, higher volume, so that tightens the joints in the ladle lining. So just like for the spinel, you have to choose the right amount of alumina and silica raw materials with the right reactivity at whatever the operating temperature is. And then you have to figure out how much mullite you actually want to form. So alumina plus silica equals mullite. We went over this quite a bit when we talked about aluminosilicate refractories. So there are various ways to do this. So you have a variety of choices on how to form mullite. You can use clay and a reactive alumina, and that gives you the desired reactivity at the operating temperature to form how much mullite you desire. So a clay might be a kaolinite clay. It decomposes to form this metakaolin. So kaolinite is Al2O3, 2SiO2, 2H2O. It forms metakaolin, which is Al2, 2SiO2, and then the water of hydration also comes off. So you need to add alumina to convert this metakaolin uh, to mullite. So you just have to add the right amount of alumina to increase the alumina silica ratio from 1 to 2 to 3 to 2. You can also start out with sillimanite and a reactive alumina. And again, you have to put the right amount of these reactive materials into the matrix to form the desired amount of mullite. So when we talked about sillimanite, it decomposes to form mullite and silica. So Al2O3 SiO2 is sillimanite. It'll form mullite, 3 Al2O3 plus 2 SiO2, and then there's some free silica. So you have to add the right amount of alumina to react with this excess silica, again, to form mullite. Uh, Another example for forming a microstructure is how you pick the aggregate. So an example here is the substitution of fused MgO in the coarse aggregates for sintered MgO. And this might be in a resin bonded MgO carbon composite for a basic oxygen furnace application. And we had talked about this. The fused MgO coarse aggregates have larger crystals than a sintered MgO aggregate. And the larger crystals reduce the grain boundary area. And the grain boundaries are the areas that are attacked and corroded first. So less grain boundary area than a sintered MgO aggregate if you start out with a fused MgO aggregate. Fusion cast aggregates have much lower porosity, so that less surface area to contact a slag or molten metal, so that decreases the corrosion rates. And when you substitute a fused MgO for a sintered MgO, that's going to overall increase the corrosion resistance, whether it's a slag or molten metal. Another example of how you can alter the microstructure is you can infiltrate a porous MgO fired brick with a pitch or a resin to create a carbon material. And this again would be for a basic oxygen furnace. So an MgO fired brick might have 15 to 20% porosity. You put that brick in a vacuum, and then you add a molten pitch or a fluid resin, and these materials are then pressurized to fill the pores. Then you heat treat this to coat the resin or pitch, or leaves carbon in the pores. The carbon is material that's non-wetting to slags and molten metals. So a non-wetting material is going to improve the corrosion resistance. And I think this may be the last example I have for microstructure control, but it has to do with particle packing. So the particle size distribution has a large effect on the final properties of a fired brick or even a refractory castable or monolithic. And we talked about gap sizing and continuous sizing. Gap sizing is more used in a fired brick. Gap sizing has low flowability, but when you make or manufacture a fired brick, you go through a pressing cycle, and that pressure um, alleviates the problem with flow control. The continuous sizing is for castables, where this size distribution, if it's continuous, allows for flow. So in gap sizing, not all of the particle sizes are utilized. Um, just the sizes that fit into the open voids or interstices that are left when a larger aggregate is packed. So these usually produce refractories with 10 to 20% porosity. Porosity usually improves thermal shock resistance. It decreases thermal conductivity, but the lower porosity also improves corrosion resistance. So for particle packing, for gap sizing, the common practice is to use 3 coarse size fractions for fired bricks. So this is an example for a fire clay aggregate, and there are 3 sizes here. A is 0.25 millimeters, B is 0.25 to 2 millimeters, and C is the coarser fraction, 2 to 5 millimeters. So here's a ternary diagram for A, B, and C. And then the numbers here are the densities in grams per cubic centimeter, but they're multiplied by 100. So the dots represent mixtures of these 3 aggregates, and then their resulting densities. So you can see right here, this is 1.765 grams per cubic centimeter. That's the highest density achieved with these aggregates on this ternary phase diagram. Then you can see the density contours that were drawn out from the center here. So this is the maximum density in the center. And then as you go out in these density contours, they tend to decrease. So this is a very simple way of maximizing or figuring out what your maximum density is when you have a certain array of sizes, and this is gap sizing. So once you have the coarse aggregate gap size, then you pick a matrix particle size, which would be a very fine particle size, uh, usually consisting of fine reactive particles. So these last very fine particles infiltrate the final pores that are present in a gap size material. And for the monolithics, you usually use a continuous size fractions. So in continuous sizing, the next size finer fraction just occupies the interstitial gaps in the previous larger size. And then you would finish up with very fine reactive or ultrafine particles, usually a reactive alumina or a fumed silica. they increase the flowability and they also form strong ceramic bonds when they react. So this might be an example of uh, some different types of castables. This is a low cement castable, and then this is an ultra low cement castable. So these are based on alumina. So the first four size fractions are the coarser fractions, 2 to 4 millimeters, 0.5 to 3 millimeters, less than 0.4 millimeters, and then 75 microns. These aren't all that different for either composition and the weight percentages. And then you have a reactive alumina and another alumina that's calcined, probably not as fine as the reactive alumina. You have a fine particle size fumed silica, a row alumina, which is very reactive. And when we talked about row aluminas, they're hydratable. So you see there's 0% in the low cement castable, but a little bit, a 0.5% in the ultra low cement castable. That hydrates and forms a bond and improves the strength. CaC is a calcium aluminate cement. The low cement castable has about 6%, and then the ultra low cement is only 0.5%. So it's relying on a small amount of the CaC cement and the hydratable alumina to form the low temperature bonding. And the water content in these are only 4%. So these are low water contents. Uh, the lower the water content, the lower the porosity. After curing, the higher the strength. Conventional castables may have 15 or more percent water. So these particle sizes are for continuous packing, create a dense material. The low cement contents require much lower water contents. So in terms of engineering design, um, the type of refractory that's selected is going to be a function of the vessel that's being used for the particular application. So what usually happens here is you line a vessel for a particular application, and then after the campaign is over, you examine the refractories. You look for the areas where the wear was the greatest, and then you try to make the next lining an improvement by uh, uh, selecting a better set of refractories if there are wear issues. So after each campaign, you want to analyze the weakest portion of the lining, identify what went wrong with that part of the lining, and then you pick a new refractory choice for the next lining, and you keep doing this until you keep improving the campaign life of whatever application you have. So one thing to consider is the heat flow, and we'll look at a traditional two-layer refractory lining for any type of refractory vessel. So these usually have two requirements. Containment of the contents of the processing vessel. So you have to contain the corrosive materials. So whatever lining you choose for that particular application has to be chemically inert to the contents of the vessel, whether it's a liquid glass, slag, metal, or even the type of atmosphere. And you want to retain the thermal energy within the processing vessel. So that's a function of how much insulation you use. So in this traditional two-layer refractory lining, you have a working lining, the inner lining, and then the outer lining is the insulating lining. So the working lining is the lining that's in direct contact with the contents of the vessel. And this gives you the corrosion resistance. The insulating lining is in direct contact with the vessel shell, and that's going to give you your thermal insulation. So this is just a diagram of a two-layer refractory lining. This is the working lining. It has thickness L1, and the thermal conductivity is K1. This is the insulating lining, thickness L2, and then its thermal conductivity K2. So this would be the hot face, the highest temperature T1. This would be the cold face, the lowest temperature T3. And then at the interface of the two linings, there's another temperature T2. So if you want to calculate the heat flow per unit area and time, Q for this lining, Q just equals the temperature difference T1 minus T3, and then that's divided by L1 over K1 plus L2 over K2. And L again is the thickness, and K is the thermal conductivity. So 1 would be for the hot face and 2 would be for the backup insulation. So to show you how this equation works, we can make a table here for the relative heat loss. So K working lining over K insulation is the ratio of the thermal conductivities of the working lining to the insulation lining. So here's a 2-to-1 ratio, a 5-to-1, a 10-to-1, and a 20-to-1. And then the ratio of the thicknesses of the lining, X would be the working lining thickness, and the X working lining, and X insulation would be the thickness of the insulation. So those ratios are 1-to-5, 1-to-2, 1-to-1, 2-to-1, and 10-to-1. And infinity, that means there's no backup insulation. It's just the working lining. So when you use that equation and calculate the various numbers, up here is the lowest, 0.109, and over here is the highest heat loss, 2.0. So a couple of examples here. If you go from a ratio of the working lining conductivity to the insulation lining conductivity, you go from 10-to-1 to 20-to-1. So you put in a much higher conductivity working lining, you double this number. So it goes from 1 to 2, going from a ratio of 10-to-1 to 20-to-1. So the heat loss is twice by doubling the working lining conductivity. And then if you go from a situation where there's no insulation to just 10-to-1, so 10-to-1 is the thickness of the working to the insulation lining. So it's primarily a working lining. But just putting a small amount of insulation in the 10-to-1 ratio, you go from 1 to almost a half, 0.556. So you cut the heat loss in half with a small amount of insulation. And then if you go to a 2-to-1 ratio, so a much more insulation, you go from 1 to 0.25. So you cut the heat loss by quite a bit to one quarter of what it was. So those are a couple examples of a two-layer refractory lining. You can also have a three-layer refractory lining. So there are three requirements here. Containment of the contents of the processing vessel. So that's simply the containment of whatever type of corrosive material you have. And again, the lining has to be chemically inert to whatever the vessel contents are. You're concerned with retention of thermal energy in this vessel, so you have to have a backup insulation. And then a lot of vessels will have a safety lining. So that's the lining between the hot face or lining and the cold face insulation lining. So if the containment lining at the hot face has a failure, you have a backup lining right behind it. That's the safety lining. So the safety lining doesn't contribute a great deal usually to the insulation, but it is chemically inert to some extent as the containment lining. So the working lining is in direct contact with the contents of the vessel. That gives you corrosion resistance. Again, the insulation lining is in contact with the vessel shell. That provides a thermal insulation. And then your backup lining is between these two linings, the working lining and the insulation lining. And that's a measure of safety if the working lining fails, but it also provides some additional thermal insulation. So this is what it would look like. You have your working lining, your backup lining, and your insulation lining. So the working lining is K1 for its thermal conductivity. The backup lining has a conductivity of K2, and then the insulation lining has a conductivity of K3. And each one has a corresponding lining thickness, L1, L2, or L3. So there's a hot face temperature T1, a cold face temperature T4, and now you have two interfaces. The temperature between the working lining and the backup lining would be T2, and the temperature between the backup lining and the insulation lining will be T3. So depending on the conductivities and the thicknesses, these temperature profiles will be altered. And again, I mentioned that sometimes you don't want um, a very shallow temperature gradient in the working lining. You don't want to back it up with enough insulation to make this a shallow gradient to make it hotter in the hot face region because that may enhance the corrosion rate. So the heat flow equation becomes T1 minus T4, the hot face minus the cold face temperature. And then for each one of these linings, the thickness divided by the conductivity. So L1 over K1 plus L2 over K2 plus L3 over K3. So that equation will give you your heat flow. So on these multi-layer refractory linings, um, you usually design them to minimize the heat loss. And the lower the heat capacity of these materials, the better they are. They're used in a thermal cycling situation. Um, when we talk about properties, that's the third course in the sequence. Um, you'll see that you don't have a large choice in the varying the composition to vary the heat capacity. The heat capacities are pretty similar for a lot of the refractory materials. So this is just the same diagram. And again, how you pick the thermal conductivities of these materials and how you change the lining thickness, you're going to change this temperature profile. If corrosion isn't a big issue, if maintaining the furnace, the heat, um, you might have more insulation. But if corrosion is an issue, you want to keep this temperature profile in the hot face as steep as possible. You want a more steep um, temperature gradient to slow down the corrosion rate. There's a freeze plane behind the hot face. So the closer that freeze plane is to the hot face, you really limit the corrosion. So the steeper the gradient, you move that freeze plane closer to the hot face and you decrease the corrosion resistance. So when you're looking at this equation here, this last term is important for controlling the thermal gradient at the hot phase. So for L3, the thickness of the insulation, the thicker the insulation, the higher this L3 number, that decreases the heat flow. Also, if you pick a low conductivity material, lower the value of K3, that also lowers the heat flow Q. Another item you have to consider is the expansion allowances. So when you heat up a lining, there's thermal expansion, irreversible thermal expansion. There's also reversible expansion. We talked about reactions that can take place, such as forming spinels or forming mullite. So there's reversible and irreversible expansion. So this takes place when you heat a lining from room temperature to whatever the operating temperature is. And we mentioned the formation of some compounds like spinel or mullite are desirable. You can engineer them or design them into the refractory lining, but you have to be aware you can develop compressive stresses if you don't design these properly. And slight compressive stresses may be desirable to create tight joints in a refractory lining, especially important in rotary kilns like rotary cement kilns or rotary calciners, and in ladles that are more cylindrical in design. So there's four sources of dimensional changes. There's reversible thermal expansion. So if the chemistry and the microstructure doesn't change during the heating and cooling cycle, that would be reversible. But if you have reactions taking place, such as mullite or spinel formation, you have irreversible thermal expansions. We talked about phase transformations that um, result in expansion or contractions. We talked about zirconia and silica. And then I mentioned creep. Creep would be permanent deformation. If the temperature is high enough, creep will take place. So there's something to keep in mind. There's a thermal gradient from the hot to the cold phase. So the temperature isn't constant across the refractory lining. There's a temperature gradient. That results in a dimensional change gradient. So these expansions, whether they're reversible or irreversible, are going to take place more rapidly and completely at the hot phase because of this thermal gradient. So how do you allow for expansion? Well, you can leave open spaces. So you can leave open spaces between the different refractory shapes, and those open spaces close at high temperatures and accommodate the expansion. You can put a spacer in that decomposes. So you place a spacer between the refractory shapes, and they decompose during heat up. A spacer could simply be cardboard that decomposes. You can put something in the joints that's compressible, like a fiber board or a fiber blanket. These have a very high porosity, so they can compress during heat up. So the equation, a very simple equation that you can use to see what kind of change in length there is during the heat up. So delta L is the length change that you have to accommodate during the heat up. A is the linear coefficient of thermal expansion. L0 is the length of the refractory structure, the width of a wall perhaps, and then delta T is your temperature change. So the change in length equals the thermal expansion coefficient times the original length of a refractory wall times the temperature change delta T. So if we look at an example for an expansion allowance with the fire clay, fire clay refractories have pretty low thermal expansions. So it's 5.5 times 10 to the minus 6 per degree C. Alumina is about 8.4 and MgO is about 13.5. So fire clays are actually pretty low. So let's take a furnace wall that's 10 meters long, that's L0, and we heat it from room temperature so that the delta T is 1,000 degrees C. So we put these numbers into this equation. So on a 10-meter long wall, the change in length is 5.5 centimeters. It doesn't sound like a lot, but if you go to this equation to calculate the compressive stress, which is sigma, that equals Young's elastic modulus E times epsilon, which is the strain. So the stress that develops sigma equals this number here, 10 million PSI. That's the Young's modulus of a fire clay refractory. And then the strain is just 5.5 centimeters divided by 10 meters or 1,000 centimeters. So when you do the division, epsilon, the strain is 0.0055. So times 10 million is 55,000 PSI. So if you make a wall 10 meters long and you heat it to 1,000 degrees C, you're going to develop very high compressive stresses. 55,000 PSI is higher than the strength of the refractory. So you have to allow expansion joints to prevent this stress from building up, because that could actually fracture the refractories during heat up. So for acid-base compatibility, you have to worry about chemical compatibility when you have different refractory compositions in contact with one another, and when refractory compositions are in contact with whatever you're processing in the vessel, whether it's a slag or a glass or molten metal. And you want to avoid acid-base contacts because acids and bases in these systems are going to react, and you want to avoid that reaction. So there's this table. This is an abbreviated table. They can be much longer. These are empirical tables. These are oxides that are ranked from highly acidic at the top here, like SO3 is acidic, going down to more basic, such as K2O. So this is an abbreviated table. It doesn't include a lot of the oxides that are present. But in this table, you can see SiO2. That's towards the top of the table. That's acidic. MgO is basic. That's towards the bottom of the table. And alumina and Cr2O3 are in the middle here. They tend to be more neutral. So you don't want to put an SiO2 refractory in contact with an MgO material. Or you don't want to put a high silica slag, an acid slag in contact with MgO. You want to put a basic slag containing a high lime content in contact with MgO. You can put a high silica slag in contact with a silica refractory because they're both acidic. And you can put a basic slag or an acidic slag in contact with the neutral refractory. So there's something known as the V ratio. And so V equals the sum of the basic oxides divided by the sum of the acidic oxides. So the basic oxides are CaO, MgO, FeO, and MnO. And acidic oxides, SaO2, P2O5. Al2O3 is usually put here. It is maybe slightly acidic, but I think it's more neutral. Fe2O3, and then Mn2O3. So if this V ratio, and these are the weight percents of each one of these components, if the V ratio is greater than 1, you have high lime and MgO present. It's a basic chemistry. If the V ratio is less than 1, you have high silica, and so on. You have an acidic chemistry. So the V ratio determines whether the system, whether it's a refractory or a slag, is basic or acidic. That table I showed was empirical. There's no good way to measure the pH of a solid refractory. It's not like in chemistry where you have a liquid and you can use a pH meter to measure the pH. You can put uh, aggregates of, let's say, lime and water and measure the pH and get a rough idea, but it's not the best way to do it. It's an empirical rating based on experience. But there's another approach called optical basicity, and that's a more scientific approach. It's new to use in refractories. I don't know how many people actually use this, but it is a pretty good approach. So it's based on Pauling's concept of electronegativity, and electronegativity is simply a measure of an atom's ability to attract electrons. Electronegativity values go from zero point 0.7 to 4. So the higher this number, the more attraction for the electrons. So 1 over lambda, and lambda is the optical basicity of an individual oxide, equals this factor here, 1.36 times En minus 0.26. So En is the Pauling's electronegativity number. You can measure optical basicity of an oxide, or you can calculate it by this equation. The measurement's not that simple. So acid base reactions, this is a periodic table, and it shows the electronegativities of all the different elements. So fluorine is 4, that's the highest. Oxygen and chlorine are also high, 3.5 and 3. So these have the highest affinity to attract electrons. Na is only 0.9, K is 0.8. So these are the lowest electronegativity values. So when you look at the total chemistry, the total chemical composition, you can calculate a bulk optical basicity. So that's beta. So that's the summation over n components, and V is the volume fraction of the ith component, and lambda is the optical basicity of that particular oxide. So you can calculate the optical basicity for the entire composition, whether it's a refractory brick or a particular slag that's in contact with the refractory. So here's the table I showed previously. This is the empirical ranking from acidic to basic. And then these are the calculated bulk optical basicities. They go from about 0.33 to 1.4. But you look at these calculated numbers, it pretty much follows the ranking that's done empirically. So it is actually a good way of calculating how acidic or basic a refractory would be, or the contents of the vessel. So this calculated number is in pretty good agreement with the empirical ranking. So if we look at an acid to base reaction for this material phosphorite, phosphorite, if you do the calculation or the empirical ranking, is a basic refractory. So it's compatible with other refractories like MgO, Cr2O3 MgO, which is a chrome magnesite, or this neutral material Cr2O3. But it's not compatible with alumina silica refractories because they tend to be acidic because of the SiO2 content. So MgO, Mg2SiO4 phosphorate reacts with silica to form liquids as low as 1500 degrees C, and then Mg2SiO4 phosphorate reacts with alumina silica refractories to form liquids as low as 1350 degrees C. So if you're going to have a phosphorite refractory in contact with an alumina silica refractory, you have to use a transitional refractory in between. Cr2O3 is neutral, so if you must use these two refractories in contact with each other, it's best to put a Cr2O3 refractory in between because it's neutral. And again, it's going to depend on the temperature where these two materials are in contact with each other. If it's low temperature, it really doesn't matter. So this is the MgO SiO2 phase diagram we showed earlier in the course. Here's phosphorite to MgO SiO2. It has a high melting point, but when it's in contact with SiO2, you can see what happens here. The solidus curve here is 1557. Over here, it's 1543. So you develop liquids at low temperatures by putting silica refractories in contact with a basic refractory, like phosphorite. So phosphorite's basic, and silica is acidic. And then if you put MgO in contact with an alumina silica refractory, you can look at this phase diagram. Here's MgO, here's silica, here's Al2O3. On the binary side of MgO and SiO2, here's phosphorite to MgO SiO2. It's right here. So if you go across this diagram and the regions over here are rich in silica and alumina, you can see you run into cordierite. It's a low temperature material. And if you look at the eutectics and peritectics around cordierite, you can see some down in the 1300s, the 1400s, and more 1400s over here. So you start running into all these low temperature regions. And then I also wanted to talk about zoning. So when you make a refractory lining for a vessel, you're usually not using just one material. You're using many different types of refractories. You're zoning the lining. So you zone it with different qualities of refractories, so different chemistries, maybe different thicknesses of the same refractory composition. And you're doing this in the different locations to maximize the campaign life of a refractory lining. So most processing vessels are zoned. So different locations have different wear rates. So different locations within a process vessel experience different operating conditions, different temperatures. They're in contact with different materials. So they need different types of refractories. So you want the entire refractory lining to have the same life expectancy or campaign life. You want the lining to wear uniformly. You don't want a portion of the lining to completely wear out and the remaining portions of the lining to have very little wear. So you want all the refractories in the lining to wear out at the same time, and that will maximize the campaign life. So for some guidelines here for zoning, you can use completely different types of refractories for different locations, depending on what the wear mechanisms are. You can use different qualities of the same type of refractories for different locations, depending on the wear mechanisms. And you can use different thicknesses of refractories for regions where the wear rates are different. So a thicker lining would be used if there's a higher wear rate. So this is an example for a ladle slag lining. So if a ladle is constructed with a single refractory, then there would be accelerated wear at most likely the slag line, the high wear area. So step one in the corrosion, the slag wets the refractory. Step two, the slag penetrates the refractory. And in step three, the slag reacts chemically with the refractory and dissolves it, and then you have corrosion. So you can use a carbon-containing refractory that prevents wetting, which is step one. So you slow down step one, that's going to slow down steps two and three. So for the same ladle slag example, you can construct the ladle with three different types of refractories based on their location. So in the barrel, in the bottom that's in contact with molten metal, you may have a different kind of refractory. At the slag line, which is in contact with molten slag, um, you use a different type of refractory. And then the transition region that separates the metal in the barrel and the slag that sits on top of the metal, you would have a different type of refractory. So you would probably use at least three different types of refractories to construct the ladle. I guess that's the last slide I have. So those are just some ideas on microstructure design of refractories and engineering design of a lining. So I guess we have four more classes left. Each one will deal with applications, and I'll go over what's now the best type of refractory for those applications and how they're zoned in the linings. And then we'll look at used refractories. I've done a lot of refractory failure. So we'll look at the microstructures of the type of refractories, the different types of refractories, and see how they're altered during use and see what the failure mechanisms are. So thanks again for listening today. And then on Wednesday for sure, we'll go over, we'll start these different linings and their failure mechanisms. So have a good rest of your day, and I'll see you on Wednesday.